We know a good deal about the evolution of the universe over the last 14 billion years. What's going to happen in the future? Right now, the universe is expanding, becoming increasingly colder and ever more dilute. For many years, the big question in cosmology had been, will expansion continue forever? Or will the universe eventually reach a maximum size and begin to contract toward a big crunch at the end of time? Debating the relative merits of these alternatives was a favorite parlor game among cosmologists ever since the early days of general relativity. Einstein himself favored a universe that was finite in both space and time, so he liked the idea of an eventual recollapse. Lemaitre, in contrast, preferred the idea that the universe would continue to cool off and expand forever, ice rather than fire. Performing measurements that would decide the question empirically turned out to be more difficult. General relativity would seem to make a clear prediction. As the universe expands, the gravitational force between galaxies pulls all of them together, working to slow the expansion down. The question was simply whether there was enough matter in the universe to actually cause a collapse, or whether it would expand ever more gradually, but for all eternity. For a long time it was a hard question to answer, as observations seemed to indicate that there was almost enough matter to reverse the expansion of the universe, but not quite enough. The breakthrough occurred in 1998 from a completely different method. Rather than measuring the total amount of mass in the universe and comparing with theory to determine whether there was enough to eventually reverse the universe's expansion, one could go out and directly measure the rate at which the expansion was slowing down. Easier said than done, of course. Basically, what one had to do was what Hubble had done years before: measure both distances and apparent velocities of galaxies, and look at the relationship between them, but to enormously higher precision and at much greater distances. The technique eventually used was to search for type 1a supernovae, exploding stars that not only have the virtue of being very bright, and therefore visible over cosmological distances, but of having almost the same brightness in every event, so that the apparent brightness can be used to deduce the distance to the supernova.